Alright, let's take a look at class example program Unit A2, page 12. As shown in video B1.2, the no-slip condition means that a fluid sticks to a solid surface. This is true for both fixed and moving surfaces. Let two layers of fluid be dragged along by the motion of an upper plate, as shown in the figure. Okay, the bottom plate is stationary, so you have two layers of fluids here. The top fluid puts the shear stress on the upper plate, right here, and the lower fluid puts the shear stress on the bottom plate, right here. Determine the ratio of these two shear stresses. Okay, first of all, let's take a look at video B1.2 first. I'm going to go back a few pages. And let's click here. So this is video 1.2. This is the water flowing from right to left, and this is solid surface. Then you're going to introduce your ink. So as you can see on the solid surface, ink sticks on the surface. It doesn't flow, just like other flow field. In order to make this ink flow, you need to literally move from the surface. In other words, on the solid surface, fluid sticks on the surface. This is called no-slip condition. Okay. So what you're seeing is flow is incoming and flowing over the solid surface. Now what happens is, obviously, on the surface of the solid surface here, you're going to develop a boundary layer. What causes boundary layer? Due to viscosity. Okay. Boundary layer is usually thin layer on the surface. Within the boundary layer, obviously at the very edge, velocity is the same as u, which is incoming flow. However, right here velocity is zero, no slip. Then between on the surface and the edge of the layer, velocity usually changes non-linearly. This is called boundary layer. That's what you're seeing. So let's just take a look at the problem. Okay, let's take a look at the problem. So this is the problem, which is fairly idealized problem here. This is a very small tiny gap, so within this small tiny gap you can assume that the velocity change can be fairly linear. Okay. In fact, a boundary layer velocity change is usually non-linear, but this is very small tiny gap, 0.02 meter. So anyways, due to the viscosity, right here, velocity is zero, no slip. But here, relative to this moving plate, velocity is also zero. In other words, fluid right here underneath of this moving plate, you have to move with 3 meters per second because it's sticking on this moving surface. Okay, again, this is no slip and no slip. As a result, between two layers of fluid, you are going to develop a velocity profile such as this. Okay, so the question is, how much shear stress is developed? Remember, for Newtonian fluid, in which in this case we assume Newtonian fluid, the shear stress can be developed due to viscosity and du dy. du dy is how much velocity change happens in the direction y. So this is direction y. So this is the velocity u as a function of y. This is not the uniform velocity. Velocity changes with respect to y. Right here, velocity is 0. Right here, velocity is u. Okay? So u at y equal to, let's say, this is delta. This is called boundary layer thickness. At the edge of the boundary layer, velocity is u. Okay? Right here, velocity right here, y equal to 0 is 0. So how much change of velocity happens in the direction y is called du dy. This is in fact how much deformation you observe of the fluid. Okay? So this is quite important equation, Newtonian fluid shear stress. So let's apply this equation for the layer of fluid 1, fluid 2. Okay. So let's begin with fluid 1. So tau 1, this is a top plate. So tau 1 is a top plate, means that you are going to set, let me just do my figure here. So this is the case we are dealing with. So this is y equal to 0, y equal to 0.04 meter. Right here is y equal to 0.02 meter. This is the velocity u equal to u, which is 3 meters per second. Right here, velocity u equal to 0. Okay? So tau 1, what I mean, top plate is tau 1 is tau at y is equal to 0.04 meters. Okay? Which is equal to mu1 du1 dy at y equal to 0.04 meters. Okay? So you're going to evaluate du dy at the specific location you're looking at shear stress developed. Okay? Now, interesting thing about it is du dy is essentially the slope. Slope means how much velocity change happens for the change of y. It's a linear function. So slope is a constant in this region, that region. This is region fluid 1, fluid 2. Okay? So du dy really is this slope. So this is how much change of velocity happened. This is du. This is how much change of y, du dy. Can you zoom in and see it? Du dy. So that's the slope. Since this is a linear function, this is a constant value within region 1. Again, constant value in region 2. This is a dy, du. Okay. So due to the fact that the du dy is constant within fluid 1, fluid 2, this really is meaningless, because if you take y equal to 0.04 or y equal to 0.02 or somewhere in the middle, du dy is always constant value. Okay. But this is quite important if you're dealing with this kind of case. Suppose if the velocity change is nonlinear, du dy depends on the location. and which is not constant. du dy is usually maximum value at y equal to 0, and du dy becomes 0 at the edge. Du dy at y equal to delta is 0. This is edge of boundary layer. Right here, du dy at y equal to 0 is essentially max value, whatever it is. Okay? So let's be careful about the real case versus this case. This case, it's linear, so it's constant. Okay. Anyways, so because of that, let's plug in the value. Mu1 is 0.4 Newton second per meter square. This is viscosity of fluid 1. du1 dy at y equal to 0.04 meter is, since it's a linear function, du dy can be approximated by delta u over delta y, because it's linear. Okay, so let's do that. So du dy, how much velocity change happened from here to here? That's du. Right here is 2 meters per second. This is 3 meters per second. So 3 meters per second minus 2 meters per second. So 1 meter per second change of velocity. That's delta u over this much height, which is 0.02 meters. So let's understand what this means. Over this much height, which is delta y, how much velocity change happened? Velocity change from 2 meters per second to 3 meters per second over the height of 0.02 meter. Since this is a linear function, this is called du dy, the slope. Okay? Now, you can never do the same thing if this is non-linear. Okay? Of course, you have to literally find out the function velocity as a function of y, then you need to take a derivative to find out. Okay. So by the way, this is going to give you 20 Newton per meter square. Okay. So what about root 2? Tau 2. This really means that tau at y is equal to 0. Okay, so this is going to be mu2 du2 dy at y equal to 0. Once again, this is linear function, so du dy is constant in between y equal to 0, y equal to 0.02, or somewhere in the middle, always same value. Again, du dy can be approximated by delta u over delta y because it's a linear function. Okay, so let's do the same thing. Viscosity is different for fluid 2, 0.2 Newton second meter square. Because of that, velocity changed from 0 to 2 meters per second over the height of 0.02 meters, which actually gives you the same exact shear stress. So, the ratio is 1. Okay, so there are a few important things you can learn from this example problem here. This is the case. Suppose if you have a linear change of velocity with respect to the height. since this is going to continuous linear function of two layers, the conclusion of this case is within this fluid, layer 1 and layer 2, the shear stress is all uniform, always this way. So everywhere in this fluid, you are going to develop shear stress, 20 Newton per meter squared. So that means how much force do you need? You can determine that. Okay. Obviously, shear stress is shear force divided by whatever the area you're going to impose here to create the motion 3 meters per second. So suppose if you put the plate and try to move it with 3 meters per second, how much force do you need? You can determine such a thing by knowing within these two layers, constant shear stress is developed. Okay. Now this is idealized case, and which is fairly true if you have a very narrow gap, just like so. Okay. Now, this is the boundary layer. Boundary layer typically comes with nonlinear velocity profile. If that's the case, first thing you need to do is you need to determine how the velocity change with respect to the y. So this is called velocity profile. Once you know the velocity profile, then you can determine du dy by literally taking velocity profile derivative with respect to y. Then multiply by viscosity, then that's going to get you tau. Now obviously, in this particular case, tau becomes maximum value on wall, which is non-slip surface. Tau becomes 0 at the edge of boundary layer. Because of that, typically, we are going to determine wall shear stress. Wall shear stress is, of course, maximum shear stress, which is developed right here, right on the solid surface. Okay. Now later, if you take aerodynamics class L2, I believe, you're going to determine how much skin friction drag you're going to develop. Skin friction drag is essentially caused by this wall shear stress. Okay? Alright, that's it.